can't even get her together because he just looks so majestic.
It has like the big,
There's
bushy
a
face,
very
really
big
gone
dog
here.
He's so.
What a way to be
See that?
described.
Yeah, no, it's, maybe it was like, hello sphere, no solid sphere, no, wait, it's like, oh, it's all, oh, it's letter, wait, no, this is solid, we're like, which one is it?
Her sister is so cute, she's such a nice lady, but it's just like she's like doing, like she does like little experiments in class, and she gets so excited and it's so adorable, she's just like, that's just so adorable.
No.
Dude, I remember the first time. He's like, so this sphere brings in the box. He's like, we're talking about that, it's like, so, who would imagine this sphere as a silk? I was like, wait, what?
Like, why makes you?
Wait, yeah.
All right, let's go ahead and get started. I just posted an announcement to Canvas like in the last 15 minutes. But I have tests for you. So if you want the most recent test or any of the others back, I have them. So yeah, let me know. Stick around in class, and I'll get it to you. Otherwise, any quick questions about the final or anything, or, we're coming very close to the end. If you have any questions that are coming to mind, let me know. The final? I actually don't know what that room is like. It's probably about this size. Okay. So I put a quiz on Canvas that basically unlimited attempts. Basically just like the details of the final. So you can find all the information in my syllabus. It's probably the easiest points I will offer you all semester long, but this multiple choice versus free response. I grant you they're both pretty easy, but they're both easy. So yeah, next Tuesday, so 6 days from now, 7 o'clock at night, upstairs.
Exactly, like I didn't, I mean.
It was originally at 3 p.m., but I moved it to 7.
Why would you do that?
Thank you.
Yeah.
Because we have Tuesdays.
All right.
And you have to say that, loser.
No, then I'm out of here.
All right, okay, fine, let's go. So I think we left in the middle of this example here. So we're talking about how to find the area enclosed by curves, the area associated with polar curves. So did I graph this one on Desmos, I think? Yeah. So if I remember correctly, this makes like a flower. The figure is actually called a rose. It's this, Okay. I can do better. But if I remember, I had 4 petals all kind of going around the origin, right? So basically we're asking to find the area of one of those petals. And we set it up last time. So one thing I want to make sure we focus on is, are we okay with why this is the thing we're integrating? We've been dealing in rectangular coordinates for so long. And that's a much simpler looking integral. Integrate f of x with respect to x. Are we okay with why this is 1/2 r squared? As opposed to just the function itself. So that all comes from basically how you find the area of like a sector, an area of like a portion of a circle. All right. So now we set up the integral. Now let's evaluate it. I want to integrate 1/2 of cosine squared 2 theta. How do we go about doing that? What's the problem here? Where's the difficulty come from? Cosine squared. Is there a way we can handle that? Right, so we've done quite a bit of this, not terribly recently, but cosine squared of theta equals what? Sorry, cosine 2 theta equals what? So there's a few different flavors, cosine squared theta minus sine squared theta. Or if we use one of the Pythagorean identities, we get 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. I don't think it terribly matters which one we'd use, but actually one's gonna be a lot easier. Which one should we go for? Which one's gonna help us get to the end? The what? Should be the second one, right? Basically, our issue is cosine squared. We don't have a sine squared to deal with, so. Now let's do this. Let's solve that cosine squared. Let's try to isolate the cosine squared. And what do we get? We get cosine of 2 theta plus 1 equals 2 cosine squared theta, or cosine squared theta equals 1/2 plus 1/2 cosine 2 theta. So that should take care of the difficulty, but how do we use that? Why are we using the identity at all, or why do we use that? Good question. Why did we use that one?
Take cosine squared and turn it into just cosine.
Right, so this is the issue. The fact that I have a cosine squared, I'd really like to reduce the power on that cosine. I don't have a sine to deal with, so I'm gonna use the one that basically picking the tool for the job. I only have a cosine squared that I have to manipulate. So that's where we're gonna choose the middle one. What happens to that cosine squared of 2 theta? What does it become? Should 1/2 plus 1/2 of cosine something, right? Right, so the angle doubles. It already was 2 theta. I'm gonna double it. Is this integral something I can handle directly? Is it okay if I take the 1/2 out? All right. So from here, what happens? Do I have space below? Let's see. Yeah. What's the integral of 1/2? 1/2 theta. What's the integral of 1/2 cosine 4 theta? So the integral of cosine is sine, right? How'd you get 1/8? Yeah, so you could do a quick substitution. I know when I take the derivative of cosine 4 theta, I'll get -4 sine. So instead of multiplying by 4, I'm gonna divide by 4. So that becomes 1/2 times a fourth, which is 1/8. And then I'll evaluate this thing. So something, Caleb?
Negative.
It actually should be positive.
Yeah, we're going from sine to cosine thing.
All right, so I think that's a good antiderivative. Questions there? Now we evaluated both endpoints, so 1/2 times 1/2 of 3 pi over 4 plus 1/8 of sine of 3 pi. What is sine of 3 pi? That should be 0. And then minus what? 1/2 of pi over 4 plus 1/8 of sine of pi, which should also go to 0. So a lot of this goes away. So what am I left with? 3 pi over 8 minus pi over 8, so 2 pi over 8. All told, I think it's just pi over 8. So yeah, just to recap, we set up the integral last time. But I think to compute it, you really do need, or to find exactly, I think you do need to apply that double angle identity to reduce the power on cosine to theta. How are we doing? All right, how about this one? I want to find the area inside one. Basically, I have these two curves, so I want to find the area that lives inside one of them and outside the other. How would you like to start? You want to see a graph? Right now, I'm gonna say no. So I think we can find where this region is without graph. Algebra. Right, so if I want to find the area, I can find out, you know, basically I can find where they're bounded by setting them equal to each other. How come I'm not allowed to draw? Okay, all right, so 3 sine theta equals 1 plus sine theta. From there, I get 2 sine theta equals 1. Or sine of theta equals a half. What angles give me a sine of a half? So quadrant 1 and quadrant 2. 30 degrees, pi over 6, 5 pi over 6. So I believe that that's some good information. What are those 2 angles going to give me? Like, how are those going to allow me to keep going? Those are my bounds. So let's remind ourselves what the integral looks like. I'm going to integrate from, I think I called it theta naught, theta 1 of 1/2 r squared theta. No, 1/2 r squared d theta. So I do have my bounds now. So the bounds from pi over 6 to 5 pi over 6 of 1/2 something. What is the r I'm going to use here? What's that? I don't think it's going to be either one of them on their own. It's going to have to incorporate both. So a good analog for this that I can offer you is think about what the way we integrate, like go back to rectangular coordinates. How do I find the area between curves? Subtracting what? Right, I can subtract the top from the bottom. I can't do that quite as directly, but what I can do is this. Basically, I'll have an outer function and an inner function. I will have something that gives me a greater radius and a lesser radius. If I find out what those things are, I can set the inverse. So I have 2 radius functions, right? Right, so right now I don't think we know which one is the greater. So how can I find out which one's greater? Y pi over 2. Right, so any value between those 2 is going to be good. So R1 equals 3 sine of pi over 2, which is what? 3. R2 is equal to 3, nope. 1 plus sine of pi over 2, which is 2. So R1 is greater than R2 inside that interval. So from there, yeah, let's set up the rest of this integral now.
Does the language of the problem also indicate that? Like, would you know, because it says inside of R1 then inside of R2, so wouldn't that imply that R2 has to be inside of R1 and R1's?
That's probably a safe bet. The only thing that I would be wary of is there might be places here like where, like if I switch the words inside and outside, I think there are other regions to make that. But I suspect that you're right. Doesn't hurt to double check. Fine.
Why did you choose pi over 2?
Good question, Glenn. Why did you choose pi over 2?
Well, for the sine is 3 easy values, so just sine of pi over 2 is 1, and then it's between pi over 6 and pi over
Right.
6.
So
So
the convenience is a nice to have thing. The thing that's a must is the fact that pi over 2 is strictly between these. So I need to pick something that's strictly on the inside of the interval. Once I find that, I'll know which is greater everywhere inside the interval. All right, so now that we know which one's greater, how do I set up this integral? 1/2 times what?
3 sine theta squared.
So for now, yeah, just leave it unsimplified. 3 sine theta squared
Minus 1 plus sine It is.
How are we doing with that? Okay. Hopefully it simplifies for us a little more. So the integral from pi over 6 to 5 pi over 6. I'll pull the 1/2 out again. That comes out to 9 sine squared theta minus 1 minus sine squared theta minus 2 sine theta. So 8 sine squared theta minus 2 sine theta minus 1. I think that's about as simple as we're gonna make it. Double check me. Make sure you agree with what I have. Any questions about how we got there? But
Where did the eight come from again? I didn't see that.
so that comes from the combination of I have 9 sine squared and a -1 sine
Oh,
squared. So that was the only thing that I was able to combine from. What else? Would you be terribly offended if I left this at the setup? So let's do that, but let's talk about where you would go. If I asked you to evaluate this, is that something you can do directly? Yes. There's at least one thing you need to do that.
So how would go identity for some.
Right. So I think anytime you have a sine or a cosine squared. I'm hesitant to say always, but you're probably gonna have to rely on. This identity, so cosine 2 theta equals cosine squared theta minus sine squared theta. And remember, you can use the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. So write that in a couple of different ways. But anytime you're trying to reduce a power on sine or cosine, you're most likely gonna have to use that. How are we doing? Sebastian?
Finding you would give us the.
I will give you that identity for sure, absolutely. What else? Okay. All right, I would like to find where these two curves intersect. I want to know where they cross, where they intersect, what do I have to do first? Set them equal to each other, so cosine of 2 theta equals 1/2. Now what? Take the arc cosine of both sides. It is totally allowed. Algebra says I can do whatever I want as long as I balance it. So what's the arc cosine of cosine? Those are inverses. What is the inverse cosine of 1/2? Should be pi over 3. Which means that theta is equal to what? Pi over 6. There should be lots of values, right? There should be an infinite number of values. So this is, I believe that doing the arc cosine like that helped us find one of them, but there should be a lot more. So let's talk about how to get those. So we know trig functions are periodic, they just repeat indefinitely. But we know that one of these things is going to happen at pi over 6, right? Actually, I'm gonna work back with, 2 theta. So when I have 2 theta. The cosine of this is 1/2, right? So 1/2. Radical 3/2, hypotenuse is 1. How often am I gonna get those? Like. There's gonna be infinitely many occurrences where I have this radius of 1/2, or I have that cosine value of 1/2. But how often are they gonna show up? Maybe I'll ask it this way, when's the next time I'm gonna have that radius of 1/2? Or a cosine value of 1/2? So if I follow this unit circle around. What's that? How'd you get 11 pi over 6?
That's the cosine value still needs to be positive. So we have to go back around to where we have a upside down triangle, but the cosine value is still positive.
So it's worthwhile to know that. Couple things, cosine is tied to the x coordinate of whatever these points are, right? So if we got one at pi over 6, we should get another one in the 4th quadrant. It's gonna have the same pi value. So can I say this then? 2 pi is equal to pi over 3 and shouldn't be 11 pi over 6, right? Should be 5 pi over 3. So maybe I wasn't clear enough about this, but I'm trying to work with 2 pi. I'm trying to do all, like, I'm trying to find out where these angles are before I cut them in half. So if one rotation around the unit circle is 2 pi, basically I'm looking for all these angles between 0 and 2 pi. But now I think I've found the only 2 there are. What if I go beyond 2 pi? When's the next one of these going to happen? How'd you get 7 pi over 3? Right, so basically 2 pi plus these things, so 7 pi over 3 and 11 pi over 3. And really these continue indefinitely, right? So yeah, I'm with you that if you do the inverse cosine, the problem with doing the inverse cosine so early is I'm only gonna get one angle out of it. And it might not be clear how to populate the rest of it. But now that I have these 4 different angles, can I find theta now? If 2 theta equals, if 2 theta equals pi over 3, then what's theta equal? Pi over 6. I can cut these all in half now. Can I generalize this though?
Pi over 6, that's 2.
So I got 1 vote for pi over 6 plus 2n pi. Where n is an integer.
Pi over 6 plus 2.
And then also 5 pi over 6. Right. So I'm writing these down. What do you think? Is that complete? Is that enough? Is that accurate? So if I have pi over 6 is the solution, right? If I add 2 pi to that, I get 13 pi over 6. That will also be a solution, right? But I think I skipped one. I think it's simply pi n. Does that cause a problem for you? Does that like make intuitive sense, or does that bother you? Okay, so we know that the cosine has a period of what? So basically, if I let theta change by a certain amount, it'll just repeat. What is that amount? If it's just cosine theta, it's 2 pi. But we have cosine 2 theta, so what's the period of that? That's simply pi, just one pi. So once we kind of found our two base solutions of pi over 6 and 5 pi over 6, we're gonna get solutions every pi after that, every integer multiple of pi. So I think the most general way to say what our answers are is these two statements here. How are we doing? Okay. Let's do one more. So I want to find where they intersect. What should I do? Again, set them equal to each other. 1 plus cosine theta equals 1 minus sine theta. Anything, where should I go from there? Okay, so I get cosine theta equals negative sine theta. Now you're stuck. Are we stuck? Oh, how are you doing that?
Because the only place that cosine of theta and sine of theta have the same values at pi over 4, but you need one to be negative.
Okay, so you're,
So-
but do
so
you
I
agree?
guess it's not 3 pi over 4, it's 5.
Okay, so you're kind of looking, you're thinking about where sine and cosine are the same and
Yeah.
working from there. And if you notice that, that's awesome, but what if you don't? Like, divide by what?
Yeah, sine, cosine,
Okay,
and
right, so that is. Algebraically, I think that's the most direct way to go forward. Don't divide it by different things. So if I divide both sides by cosine, I get 1 equals what? Negative tangent theta. Or tangent theta is equal to negative 1. Back to my terrible unit circle drawing. In what quadrants are the tangents of angles negative? 2 and 4. So here and here. And kind of like Caleb was alluding to, they're only equal, at least in magnitude, when these angles in here are both what? Pi over 4, 45 degrees. But now we got to figure out what those angles are in those quadrants. So they are what? 3 pi over 4, 7 pi over 4? Are those the only two? So I mean, they're gonna show up every 2 pi or every 2 pi after those, right? So that and then 15. So where can we generalize that? I can't write down these angles all day. 3 pi over 4 plus n pi. Is this a symbol that you all know? Okay, you're gonna learn it right now. That like fluffy z is the set of all integers.
Isn't it still not 3 pi?
In this case, it is 2 pi, but that's not inclusive enough. I am gonna get solutions every 2 pi, but I'm also gonna get them every single time. So there's 2 solutions, but also, we talked about sine and cosine having a period of what? So by period, I mean, just refresh from. I'm sure you've heard it before, but the period of a function is basically what the change in the input has to be for that function to repeat its behavior again. So for sine and cosine, what is that period? 2 pi.
So would it be 2 pi if we like the last one where we did 2 different?
Yeah, so the key here is that this came from a cosine, right? The last one. This one comes from a tangent. The tangent does not have a period of 2 pi. Has a period of time. And then you can tell from, or I'll point it out from my diagram here. How far apart exactly are these two solutions that I kind of indicated? Pi. So I could have written 3 pi over 4 plus 2n pi, and 7 pi over 4 plus 2n pi. But they can both be absorbed at the same state.
Also, what's that weird thing?
Oh, sorry, that's another symbol you probably haven't seen. This means is an element of, n is an element of Blackboard Z, which is the vendors. It's a Z because the Germans got to it first, and I don't know what the German word is for integer, but it starts with a Z. What else? All right, arc length. Last thing I'm going to show you all semester long. So let's relate it back to Cartesian coordinates. Something we did a while ago, did a lot of it. How do we find arc length in Cartesian coordinates? So it's an integral from, some place to some other place. So that's the first flavor that we kind of looked like this, right? We made a slight modification to this for parametric curves. What did that look like? Right. So hopefully those seem familiar. One of those is from a while back. One of them is very recently. But essentially, now we're going to derive something similar for polar curves. So in a lot of ways, theta is a parameter. We don't really treat it the same way. It's got a lot more properties to it that are unique to circles. But for now, let's talk about polar curves having this integral. So dx d theta squared plus dy d theta squared. But we can do a little bit better than that. If you remember from Monday, if I give you a polar curve and I ask you to find dx d theta, it's deceptively involved, right? There's a lot that goes into it. So let's try to find a workaround. What are x and y equal to in terms of, going back and forth between polar and rectangular coordinates? So x is r cosine theta and y is r sine theta, right? So then if I want to find dx d theta, what is that? We can either do it from scratch right now, or we did it a lot on Monday, if you remember it, have it written down. What do you need to find that derivative? Like, what techniques do you need to rely on? You use product rule, right? So let's do that. So this becomes, for now, because I'm going to be doing a lot of manipulations, I'm going to call this r prime cosine theta plus r, nope, minus r sine theta, right? And then dy d theta becomes r prime sine theta plus r cosine theta, right? So let's pause there for a second. Does that look familiar from Monday? If it doesn't look familiar, can you at least see where it came from in this moment? Okay. So now that I have those derivatives, let's drop them into this integral and see what happens. The square root of dx. So what's dx d theta squared? That'll be r squared cosine squared theta, not r squared, r prime squared. What's that?
What difference does it make?
So yeah, how are r and r prime related to each other? Yeah, one's a derivative of the other.
Will that mess it up when we're doing
Mess it up how?
Make it more complicated or just?
For now, it will be, but I promise it's going somewhere useful. Plus r prime squared sine squared theta. And then the middle term is going to be minus 2r prime sine of theta cosine theta. With me so far? All right, now I'm going to square the other one. Plus r squared sine squared theta. Did the same thing again, r prime squared. I made a mistake in the top line, didn't I? This middle r prime should just be r. Plus r squared cosine squared theta. Plus 2r prime sine theta cosine theta. So I got 6 terms in that mess. I'm gonna put parentheses on them because they really are all included under the square root. So yeah, what's really complicated right now, is there anything convenient that happens from this? So the third and the sixth terms annihilate each other. That's good.
Factor out r squared. Sine squared of theta and cosine squared of theta, those go to 1, and r prime squared of theta, you r prime squared. If you factor that out as well, you'll get another cancellation of cosine.
So I have the square root of r squared times sine squared of theta plus cosine squared of theta. Plus r prime squared times sine squared of theta plus cosine squared of theta.
Are you factoring that out?
How am I?
Yeah, 'cause there's the R prime and the R.
The r prime. Well, okay.
They're grouping together.
So yeah, I'm not factoring the r squared or everything, just the things that I can. So these two terms here are collected here, and then those there are just like this leftmost column. What did that do for us? That goes to 1, that goes to 1. So this nasty integral ends up looking a lot simpler. So the integral from b to a of this, the square root of r squared plus dr d theta squared d theta. So in finding the arc length, we don't actually have to deal with the dy d theta, dx d theta, because those are, because of the product of those get complex quickly. So now we've derived it, you're free to use it kind of as is, but I wanted to show you where it came from. How are we doing? Shall we use it a couple times and call it a day? No, any questions?
So when it's the R theta, are we differentiating like the R then instead of the theta?
Yeah, so what does that symbol dr d theta mean?
It's that derivative. But you're drawing with respect to R.
Not with respect to r. So r is the thing I'm taking the derivative of.
Oh, wait, D theta.
Yeah. So what I suspect you're looking at, what I suspect you're trying to confirm is the derivative you want to take. It's the more convenient one to take.
Yeah.
So like this right here. If I asked you for dy dx of that curve, that would take us, I mean, we can do it. Takes a while. What's dr d theta for that r? Yeah, we're in that one. So that's why having that integral is a lot. Yeah, in that form is a lot more convenient to use. So I want to find the length of this cardioid. How do we set that up? So we just derived this thing. So the integral from a to b of the square root of r squared plus dr d theta squared d theta. So I've given you r. We just said out loud what dr d theta was. So we've got most of this integral set up. So the square root of one plus sine theta squared plus cosine squared theta d theta. But what else do we need? We need the bounds, right? How do we get the bounds? I don't know if I've used this phrase before, but do you know what it means when I say a curve is closed? I know I briefly put it on like the last homework. Yeah, so basically like a circle is a closed curve. You can trace around it as many times as you want, but you're just tracing over it. We can think of this as a closed curve. So I can map it out between two theta values. But if I kept letting theta grow, I would be tracing over the thing I've already traced, right? So I have r equals 1 plus sine theta. Give me an interval that would work to trace. Basically, I want to find the length of this thing only once. I want to find the length of the whole thing, and I want to find the length of no more than one trace of it. Why do you believe that?
Because it's gonna have the same value at 0, it's gonna have the same value at 2 pi.
Why will it have the same values?
Because sine of 0 is 0, sine of 2 pi is 0.
So it's a sine wave. I know a lot about the period of sine waves.
Or is it 0? Because that would also give you the same value.
It would, but that's not enough, right? So let me draw you a sine wave.
Zero two, I would hit the same points in the circle. Would you just?
Right. So here's your sine wave, right? I agree with you that this and this are both 0, right? But in between those two big dots, is that a period? No, it's not. It's half a period because, yeah, after this middle dot, it's not going to continue the behavior it was doing at the start of the other one. So we're not going to do this, but I think this is also a good interval of 17 pi to 19 pi. All that really matters is what? That I have a width of 2 pi. Go ahead, Sebastian.
Are like functions of mixed free, or like you have to be more careful about the bounds. Like,
Yeah, so if that was 1 plus sine of 3 pi or something, then I want to take a look. So I could bring up an example from Monday. A while ago, but it was this one here. I am positive that when I asked about this, the bounds that were first suggested were 0 and 2 pi. Because we're just very used to that being like, it's a trig function. I know how those work. I know when they stop and when they start again. But this one was not so much because we actually had to look at. I think I did show you a graph on Desmos of this. This one, I'm telling you, we can safely go with these bounds though. Is this an integral we can do? So let's simplify a little bit. What do we come up with? One plus sine squared theta plus 2 sine theta cosine theta plus cosine squared of theta d theta.
Sine theta equals sine theta.
That comes from the middle term of expanding that binomial. It's not cosine theta.
It wouldn't just be 2 sine.
Yeah, it would be. Here's the cosine squared of it, cosine part of it. Right, so what happens in there?
Sine plus radius.
Right, so I end up getting the square root of 2 plus 2 sine theta. How are we doing? For our purposes, I am happy to call that. Good, so that is like many things we talked about, the setup of the integral is far more important to us than going through the manual computation of that, that's gets out of hand quickly.
Is there such easy way to do that?
Depends on what you mean by easy,
Or like straightforward?
symbol that.
On the test, if we leave that and then mess up our calculations, will we get more points because we got that right?
Absolutely, I mean, if it's a very response, absolutely. Does that answer your question?
Oh, I was just gonna ask if we can date this down, if it was that hard.
Depends on what I'm asking you for.
How do we know, like, from the question, if you're okay with this?
We have to be very deliberate in the way we ask it. Because I don't expect that to be obvious to you that is deceptively difficult. And I think if you remember back when we did our length with Cartesian coordinates with rectangular curves. It's very hard to like, actually, let me say it this way, it's very easy to just have you calculate an arc length and for the integral to come out gross. That's not something we're interested in having you devote a bunch of time to on a time test. So I'm happy with this setup and how we got here.
Is the same like setup as the first two tests or is it?
Yeah, essentially, it's like 50% longer. So what were the other two tests? 10 multiple choice, 2 free response. I think this one's 15 and 3. So it's same format, just beefed up 50% more on either side.
And will it focus more on the stuff after the last test?
It's pretty even. So there are only 2 sections that didn't land underneath any of the first 3 tests. It's pretty even. You'll see some stuff about this, but it's not going to be like overwhelmingly. What else? Question?
We'll be getting, just like the double angle equations for the test.
So I'll give you what you need. We got 3 minutes. Let's set this up and see if it looks convenient at all. How do we do it? Y'all ready for my last bad graph of the day? So it looks something like this. Yes, I want to find the length of that thing right there. So how do we set up that integral? So this time I kind of have to tell you the bounds. Integral from 0 to 2 pi of what? So theta squared. Plus 2 theta squared d theta. Just remind ourselves, where did this thing come from? That's r squared, and then this is what? That's the derivative. So does this give us anything convenient? Yeah, I can factor out a theta, and I get what?
Why is it not?
4 theta squared. Why is it not 4 theta squared? I would love to tell you that most of the time I do that, it's on purpose. So how are we doing with that setup then? Okay. I believe I could ask you to do that one by hand, it wouldn't be terrible. How would you go further with that? Use what would the U be?
You would be 0.
Right, what's under the radical? So that one I don't think is all that awful to do, but it's 10:59. So quick reminder before I let you all go. I put a bunch of stuff on Canvas. It's really, I just put the same link to the same like Math 266 review website. There's a PDF on there with some review questions. Last time I'll see you is Friday, so let's, whatever questions you have, come ready, and then we'll, basically I'll let you all drive the show.
Will it be same office hours?
Yeah. So I got office hours today at 1:30 and Friday at 12.